here we have to apply a growth rate of 2.95% to this principal of $3,500 over 4 years. And this problem is meant to just illustrate the idea of compounding. We're going to do it over various methods: annually, monthly, daily, ultimately continuously. So the idea of compounding is you take some initial amount and you multiply it by 1, which amounts to 100%. This way it retains what it was, plus the amount of growth. So in this case, it's 2.95%, which as a decimal is 0.0295. And then we divide it into pieces, divide that rate of growth into pieces, and that way we can apply it multiple times throughout the time period. In this case, it's years. That way it's more closely will model what is meant by natural growth. If something's growing according to a percentage, it really wouldn't wait till the end of any arbitrary time period. It'll always be growing at that percentage. So this idea of compounding is I can take the initial balance, which is $3,500, the principal, and every time I multiply it by this factor here, I'm taking the initial balance plus that amount of growth. Again, the amount of growth is divided into pieces, and that way, throughout the year, I can do that many times. So, for example, if it's asking for annually, then we're just dividing the growth rate up into one piece once per year, and in this case, I guess we'll plug in t equals 4 since it's 4 years. I'll apply this factor 4 times. Every year we grow it by 0.0295%. This is 4 years, so we got 4 factors of this. This can be done in the calculator. To do this monthly, it's the same idea, but rather than apply the growth factor once a year, we're doing it 12 times a year. So we divide it into 12 pieces, and then 12 times a year over the course of 4 years will amount to 48 factors of this. And this, again, we can do this in the calculator as well. Then they asked to do it daily, where we divide the growth rate into 365 pieces, and then throughout each year, apply the growth factor 365 times. So that's 365 times 4, since this is again over 4 years. So that is in order, the daily, the monthly, the annually, so once a year, the monthly, 12 times a year, and then the daily, 365 times a year. And the more and more times we do this, so 1 became 12, became 365, if we did it every minute, let's say every second, for example, the more often we do it, the closer we get to this idea of continuous growth, which is modeled with this function here, which is the principal, and then times this exponential factor e to the growth rate of 2.95% per time period, which again, in this case is 4 years, so put the 4 there. And this output would be continuous growth. Basically, the way this works is if you were to let this n, the number of times you're compounding, get larger and larger and larger, the closer it's going to be to this model here. We call this continuous growth. So finally, it wants the doubling time. And the way to get doubling time is to just consider the fact that, well, it starts at 3,500, so we want it to be 7,000. That would amount to doubling 3,500. So you could either put 7,500 on the other side, or 7,000 on the other side of this equation here, and then divide out the 3,500 to get your 2. Either way, doubling time, irregardless of what the initial balance was, is always a matter of setting your exponential piece to 2. So when I say exponential piece, that's the e raised to the growth rate of 0.0295 times 4 years. So solving this equation will get us doubling time. If I write this as natural logarithm, I've got the natural log of 2 is equal to our exponent of 0.0295, find the doubling time for the given interest rate. Oh, okay. I got a 4 here. I see. This is for the doubling time. We're not meant to put in a 4. We want to know how long is it going to take to double. So I'm going to need this to be a t here. And now we can solve for t. So it's just a matter of putting all the stuff into the calculator at this point. Let's see the, for example, the first one, 3,500. 1 plus 0.0295 raised to the 4th. That's that output. We could do it for, just going to copy this. We were doing this divided by 12 pieces for monthly. Oops, it's not right because if we do it monthly, we need 4 times 12 factors of this. So we need 48 factors. There we go. Looks better. Can I delete this? Let's see. Delete. There we go. Looks better there. Okay, so we got annually. And now we'll do daily. So this was 3,500. 1 plus the growth rate now gets divided up into 365 pieces. And then we're going to raise it to, we got 365 once per day times 4 years. And there's that output. And you can see these are pretty similar. The more often you compound it, the higher it is, but not by that much. Going from annually to monthly was a difference of about $6, and then monthly to daily was about, well, not even $1. And last up was the continuous, which was the E. That is this one here. So we're doing $3,500. If we want to compound it continuously, we use the base E. The growth rate was 0.0295, and that was over the course of 4 years. So there's that value there. Again, pretty close. This is less than $1. Actually, it's not even. It's like a couple cents more than what it was when we did it daily. So that's part D there. And then for doubling time, we went through the formula here, but you might even just be worthwhile to remember the formula. It's always going to be the natural log of 2 because it's doubling, divided by the growth rate. In this case, the growth rate was 0.0295. So whatever that is, that's our answer to doubling time. We could figure that out with the calculator. Natural log of 2 divided by 0.0295. So we're at roughly 23.5 years. Just round that however the problem requests. So hopefully you find that helpful. Thanks. Bye.